Look up at the night sky on a clear evening far from the glow of any city, and you will see something that has captivated every civilization that has ever existed. Stars, thousands of them. A river of light we call the Milky Way, arching overhead like a bridge between horizons. It feels like everything is there, laid bare for you. The universe, in all its enormity, puts on a show just for your eyes. But what if I told you that everything you see up there, every star, every nebula, every galaxy that has ever been photographed by every telescope ever built, accounts for roughly 5% of what actually exists? What if the remaining 95% is something we cannot see, cannot touch, cannot taste, cannot smell, and cannot hear? What if the universe you think you know is little more than a thin, luminous film stretched across a vast, invisible architecture that you have never once perceived? This is not science fiction, this is not speculation, this is the consensus of modern physics. And the name we have given to the largest component of this hidden architecture is dark matter. Now that name is a bit misleading. Dark makes it sound like it is simply matter hiding in the shadows, like an unlit room that would reveal its contents if only we flipped the right switch. But dark matter is not dark the way a cave is dark. It is dark in a far more profound and unsettling way. It does not interact with light at all. Light does not bounce off it. Light does not get absorbed by it. Light passes through it as though it were not there. And this means that no matter how powerful your telescope, no matter how sensitive your detector, no matter how clever your instrument, you will never see dark matter directly. You can only infer that it exists because of what it does to the things you can see. Imagine standing in a field on a windy day. You cannot see the wind. Wind is invisible. But you can't see the grass bending. You can see the leaves swirling. You can see the trees leaning. And from those visible effects you can deduce that something invisible is at work. Something powerful, something real, something that shapes the behavior of everything around it even though it has no color, no form, no visible presence whatsoever. Dark matter is the wind, and the galaxies, the stars, the cosmic structures we observe, they are the grass, they are the leaves, they are the bending trees. And for nearly a century, physicists have been watching the grass bend and trying to figure out what exactly is blowing. Let us start at the beginning of this story because, like all good stories, this one begins with someone noticing something that did not make sense. The year was 1933, and a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies known as the Coma Cluster. A galaxy cluster is exactly what it sounds like. A group of galaxies bound together by gravity, orbiting a common center of mass the way planets orbit a star, only on a scale so immense that it dwarfs anything the human mind can comfortably imagine. The Coma Cluster contains over 1,000 galaxies, each one home to hundreds of billions of stars, and the whole collection spans millions of light years across. Zwicky wanted to measure the mass of this cluster, and he had a straightforward way to do it. He measured how fast the galaxies within the cluster were moving. This is a standard technique in physics. If you know how fast something is orbiting, and you know how far it is from the center, you can calculate the gravitational pull required to keep it in orbit, and from that gravitational pull you can infer the mass that is generating it. It is the same principle that lets us calculate the mass of the Sun from the speed of the planets. Gravity and motion are intimately linked, and if you know one, you can deduce the other. So Zwicky measured the velocities of the galaxies in the Coma Cluster. He added up all the light coming from the cluster, estimated how many stars that light represented, and calculated how much mass those stars should contain. And then he compared the two numbers, the mass implied by the motion of the galaxies and the mass implied by the light they emitted. They did not match. They did not even come close. The galaxies were moving far too fast. Given the amount of visible matter in the cluster, there was not nearly enough gravity to hold them together. At the speeds Zwicky measured, the galaxies should have been flying apart. The cluster should not have existed. It should have dispersed long ago, each galaxy sailing off into the void like sparks from a fire. But the cluster was there, stable, bound, held together by something. Zwicky did the calculation again. And again. The result was always the same. The cluster contained roughly 400 times more mass than the visible matter could account for. 400 times. This was not a minor discrepancy. This was not a rounding error. This was a chasm between what was observed and what was expected. A gap so vast that it demanded an explanation. Zwicky called the missing substance Dunkel Materie. Dark matter. And here is where the story takes a turn that is both fascinating and deeply human. The scientific community largely ignored him. Zwicky was, by many accounts, a brilliant but difficult man. He was abrasive, he was combative. He once reportedly called his colleagues at Caltech spherical bastards because, he said, they were bastards no matter which direction you looked at them from. His personality made it easy to dismiss his work, and the idea itself seemed so radical, so contrary to the assumption that what we see is what there is, that most astronomers simply set it aside and moved on. Dark matter was treated as an oddity, a curiosity, a problem for another day. Another day would not arrive for nearly 40 years. In the 1970s, an American astronomer named Vera Rubin was studying the rotation of spiral galaxies. A spiral galaxy, like our own Milky Way, is a vast disk of stars, gas and dust, rotating around a central bulge. And just as planets closer to the Sun orbit faster than planets farther away, stars closer to the center of a galaxy were expected to orbit faster than stars near the outer edge. This is what Newtonian gravity predicts. The farther you are from the center of mass, the weaker the gravitational pull, and the slower you should orbit. Rubin was measuring the orbital speeds of stars at various distances from the centers of galaxies. She was using a spectrograph, an instrument that splits light into its component wavelengths and allows you to determine how fast something is moving toward or away from you based on the shift in those wavelengths. It is the same principle as the Doppler effect you hear when an ambulance passes you. The pitch changes because the sound waves are being compressed or stretched by the motion of the source. Light does the same thing. An object moving toward you has its light shifted toward the blue end of the spectrum. An object moving away has its light shifted toward the red. By measuring these shifts, Rubin could determine the rotational velocity of stars at different points within a galaxy. What she expected to find was a curve, a line on a graph that rose sharply near the center of the galaxy, where the gravitational influence is strongest and the stars orbit quickly, and then gradually fell off toward the edges, where the stars are farther from the center and should be moving more slowly. This declining curve is what you would predict if the visible matter, the stars and gas you can see, accounts for all the gravity in the galaxy. What she found was something else entirely. The curve rose near the center, just as expected. But then, instead of falling, it flattened out. The stars near the edges of the galaxy were moving just as fast as the stars closer to the center. In some cases, even faster. This made no sense. If the only mass in the galaxy was the visible matter, the outer stars were moving far too quickly to remain in orbit. They should have been flung outward, like a ball at the end of a string that is being spun too fast. The gravitational pull of the visible matter was simply not strong enough to hold them. And yet there they were, orbiting, stable, held in place by something. Rubin checked her measurements. She checked them again. She checked them with different galaxies, one after another, after another. The result was always the same. Every galaxy she studied showed the same flat rotation curve. The outer stars were always moving too fast. There was always more mass than the visible matter could account for. And unlike Zwicky, Rubin was not dismissed. Partly because the instruments had improved and the data was harder to argue with. Partly because the scientific climate had shifted. And partly because Rubin was meticulous, patient, and persistent. She did not just find the anomaly, she documented it across dozens of galaxies, building a case so thorough that it could not be ignored. The conclusion was inescapable. Galaxies are embedded in vast halos of invisible matter. Not just a little extra matter hidden in the corners, but enormous quantities of it, extending far beyond the visible edges of the galaxy in every direction. The luminous disk of stars that we see when we look at a galaxy is not the galaxy. It is just the bright center of something much larger, something we cannot see, something that outweighs the visible matter by a factor of 5 or 6 to 1. Picture it this way. Imagine you are looking at a city at night from a great distance. You can see the lights, the skyscrapers, the glowing grid of streets. And you might assume that the city is defined by those lights, that its boundaries are the boundaries of its illumination. But now imagine that the city sits on a vast invisible plateau that extends for hundreds of miles in every direction, a foundation that supports the city, shapes it, and determines where it can be built, but that you can never see because it emits no light. The visible city is real, but it is perched on something much larger, much more massive, and utterly invisible. That is what a galaxy is. The stars are the lights. The dark matter halo is the plateau. Now, you might be wondering why we are so confident that the explanation is invisible matter rather than some flaw in our understanding of gravity. After all, maybe Newton was wrong. Maybe Einstein was wrong. Maybe gravity does not work the way we think it does on the scale of galaxies. And if we just tweaked the equations a bit, the discrepancy would vanish without the need to invoke some mysterious, unseen substance. This is a fair question, and it has been asked seriously and rigorously many times. There are alternative theories of gravity. The most well-known is called modified Newtonian dynamics, or MND, proposed by the physicist Mordechai Milgrom in 1983. MND suggests that at very low accelerations, the kind experienced by stars in the outer regions of galaxies, gravity behaves differently than Newton predicted. Specifically, it becomes slightly stronger than the inverse square law would suggest. And remarkably, MND does a very good job of explaining the flat rotation curves of many galaxies without any need for dark matter. But here is the problem. While nothing works well for individual galaxy rotation curves, it struggles, and in some cases fails entirely when applied to larger structures. It does not easily explain the dynamics of galaxy clusters, the same structures Zwicky was studying in the 1930s. It does not naturally account for the pattern of temperature fluctuations in the cosmic microwave background, the ancient light left over from the Big Bang. And it does not explain one of the most visually stunning and scientifically compelling pieces of evidence for dark matter ever discovered. That evidence came from a cosmic collision. In 2006, astronomers released observations of an object known as the Bullet Cluster. It is actually two galaxy clusters that collided with each other millions of years ago. When galaxy clusters collide, the individual galaxies within them mostly pass through each other, like two swarms of bees flying through each other. This is because galaxies within a cluster are spaced far enough apart, but direct collisions between them are rare. But the hot gas that fills the space between the galaxies does not pass through. Gas is a fluid, and when two fluid masses collide at high speed, they slam into each other, compress, heat up, and slow down dramatically. This is exactly what was observed in the Bullet Cluster. The hot gas, which is visible in X-ray telescopes, was concentrated in the center of the collision, smeared and compressed by the impact. But here is the key observation. Astronomers also map the distribution of mass in the bullet cluster using a technique called gravitational lensing. Einstein's general theory of relativity tells us that mass warps spacetime, and this warping bends the path of light passing nearby. So if you look at a massive object and observe the way it distorts the images of more distant galaxies behind it, you can map out where the mass is concentrated, even if you cannot see it directly. It is like detecting the presence of an invisible glass lens by noticing how it bends the light behind it. And when astronomers mapped the mass distribution of the bullet cluster, they found something extraordinary. The bulk of the mass was not where the hot gas was. The hot gas, which constitutes the majority of the ordinary matter in a galaxy cluster, was stuck in the middle, where the collision happened. But the majority of the mass, as revealed by gravitational lensing, had sailed right through the collision and was located on either side, coinciding with the positions of the galaxies. This is exactly what you would expect if the clusters were dominated by a form of matter that does not interact with ordinary matter or with itself, except through gravity. The dark matter, being collisionless, passed right through the collision, just as the galaxies did. The ordinary matter, being, well, matter, smashed together and got stuck in the middle. Mount cannot easily explain this. If there is no dark matter, then the mass should be where the matter is, which is in the center where the gas collected. But the mass is not there. It is on the sides. Something invisible is carrying it. Something that passed through the collision like a ghost through a wall. The bullet cluster is sometimes called the smoking gun of dark matter. It is not definitive proof. Science rarely offers definitive proof, but it is a powerful, visual, and deeply persuasive piece of evidence that something massive, invisible, and fundamentally different from ordinary matter exists in enormous quantities throughout the universe. So let us accept, at least provisionally, that dark matter is real. That there exists some form of matter that does not interact with light, does not interact with ordinary matter except through gravity, and outweighs the visible universe by a factor of roughly 5-1. The obvious next question is, what is it? And this is where the story becomes, if possible, even more mysterious. Because despite decades of searching, despite some of the most sensitive experiments ever conceived, despite billions of dollars and the combined efforts of thousands of the most brilliant physicists on Earth, nobody knows. We know what dark matter is not. It is not an ordinary matter hiding in some hard-to-see form. It is not black hole. It is not a dead star. It is not a rogue planet wandering through intergalactic space. We know this because we can constrain the total amount of ordinary matter in the universe through a completely independent method, the process of Big Bang nucleosynthesis. In the first few minutes after the Big Bang, the universe was hot enough and dense enough for nuclear fusion to occur everywhere at once. Protons and neutrons were combining to form the lightest elements: hydrogen, helium, and trace amounts of lithium and deuterium. The exact proportions of these elements that were produced depend sensitively on the total density of ordinary matter, what physicists call baryonic matter, everything made of protons, neutrons, and electrons. By measuring the actual abundances of these light elements in the universe today, which we can do with great precision, we can work backward and calculate exactly how much baryonic matter existed in the early universe. The answer is about 5% of the total energy density of the universe. Not 27%, 5. The other 22% of the matter, the dark matter, must be something else. Something non-baryonic, something not made of the protons and neutrons that make up you, me, the Earth, the Sun, and everything we have ever directly experienced. This is a staggering realization. The stuff that makes up our bodies, our planet, our star, everything in the periodic table of elements, is a minority constituent of the universe. We are the froth on the surface of a deep, dark ocean. We are the sprinkles on an invisible cake. The universe is made mostly of something we have never identified, never held, and never created in a laboratory. So what could dark matter be? The leading candidates fall into a few broad categories, and each one represents a different bet about how the universe works at its most fundamental level. The first and historically most popular candidate is a class of particles known as WIMPs, which stands for weakly interacting massive particles. The name is wonderfully descriptive. These would be particles that have mass, potentially quite a lot of mass compared to other subatomic particles, but that interact with ordinary matter only through gravity and the weak nuclear force, one of the four fundamental forces of nature. The weak force is the force responsible for certain types of radioactive decay, and it operates only at extremely short range and with extremely low probability. This means that WIMPs would almost never interact with the atoms in your body or in a detector or in anything else. They could pass through the entire Earth without touching a single atom. The appeal of WIMPs is not just that they have the right properties to be dark matter. It is that they arise naturally in many extensions of the standard model of particle physics, particularly in a framework called supersymmetry. Supersymmetry posits that every known particle has a heavier superpartner, and the lightest of these superpartners, if it is stable, would behave exactly like a WIMP. This coincidence, that a theory invented to solve problems in particle physics independently produces a particle that could explain dark matter, is sometimes called the WIMP miracle. It felt too elegant, too perfect to be wrong. And so for decades, physicists built increasingly sophisticated experiments to detect WIMPs. The basic idea behind most of these experiments is beautiful in its simplicity. You take a large quantity of some very pure material. Liquid xenon is a popular choice. You put it deep underground to shield it from cosmic rays and other background radiation, and you wait. If a WIMP happens to pass through and collide with one of the xenon atoms, the collision will produce a tiny flash of light and a small amount of ionization. By detecting these minuscule signals, you can confirm the presence of a WIMP and measure its properties. Experiments like Snamming 1T, LUX, and PandaX have been running for years. They are marvels of engineering. They operate in mines and tunnels deep beneath the Earth's surface, surrounded by layers of shielding, in environments so quiet that they can detect the passage of a single particle. They are, in a sense, the most sensitive ears ever built, listening for the faintest whisper of an interaction between the visible and invisible worlds. And they have heard nothing, year after year. The sensitivity of these experiments has improved. The amount of material has increased. The backgrounds have been reduced. The analysis techniques have become more sophisticated. And yet, no WIMP has been definitively detected. Each new result pushes the boundaries further, ruling out larger and larger regions of the parameter space where WIMPs could exist. If WIMPs are out there, they must be interacting even more weakly than the most optimistic models predicted. This does not mean WIMPs are ruled out. There is still room in the parameter space for them to hide. But the WIMP miracle is beginning to look less like a miracle and more like a mirage. The elegant coincidence that once seemed so compelling has not been confirmed by experiment. And slowly, reluctantly, the field has begun to diversify its bets. The second major candidate is a particle called the axion. The axion was originally proposed in the late 1970s not to solve the dark matter problem, but to solve a completely different puzzle in quantum chromodynamics, the theory of the strong nuclear force. There is a parameter in QCD that could, in principle, take any value. If it had a large value, it would cause the neutron to have a measurable electric dipole moment, a slight asymmetry in the distribution of charge within the neutron. Experiments have measured the neutron's electric dipole moment to be essentially zero, which means this parameter must be extraordinarily small. But why? Why is it so close to zero when there is no obvious reason it should be? The Pesce-Quinn mechanism, proposed by Roberto Pesce and Helen Quinn, provides an elegant answer. It introduces a new symmetry to the theory that dynamically drives this parameter to zero. And the breaking of that symmetry produces a new, very light particle. That particle is the axion. It turns out that if axions exist with the right mass and the right properties, they would have been produced in enormous quantities in the early universe, and they would behave exactly like cold, dark matter. They would be extremely light, far lighter than WIMPs, but they would be so numerous that their collective mass could account for all the dark matter in the universe. Searching for axions requires a completely different experimental approach than searching for WIMPs. One of the most creative methods involves a device called a haloscope, essentially a microwave cavity placed inside a very strong magnetic field. If axions exist and are passing through the cavity, they can, in the presence of a magnetic field, convert into photons, tiny flashes of microwave radiation that can be detected with exquisitely sensitive amplifiers. The ADMX experiment at the University of Washington has been searching for axions this way for years, gradually scanning through different frequencies, each corresponding to a different possible axion mass. So far, no definitive detection, but the search is far from over. The axion parameter space is vast, and the technology is still improving. Many physicists consider axions to be the most promising dark matter candidate today, in part because they solve two problems at once: the dark matter problem and the strong CP problem, and in part because they have not yet been ruled out by experiment the way large portions of WIMP parameter space have been. But WIMPs and axions are not the only possibilities. There are sterile neutrinos, hypothetical particles, that interact with ordinary matter even more weakly than regular neutrinos. There are primordial black holes that might have formed in the very early universe from density fluctuations rather than from the collapse of stars. There are particles from hidden sectors, entire families of particles that exist in a parallel world of physics, interacting with our world only through gravity. There are even more exotic ideas, particles from extra dimensions, remnants of cosmic phase transitions, quantum solitons, and superfluid condensates. The list is long, and the experimental evidence is, so far, frustratingly silent. This is worth dwelling on for a moment, because it represents something genuinely unusual in the history of science. We have identified a phenomenon. We have measured it with multiple independent methods. We are confident it is real. And yet we have no idea what causes it. We know that dark matter exists. We know how much of it there is. We know where it is distributed. We know how it behaves on cosmological scales. And we cannot tell you what it is made of. It is as though you had discovered that your house was sitting on a foundation, that the foundation was supporting everything, that without it the house would collapse, and that you could measure the weight and shape and extent of the foundation with great precision. But when you tried to dig down and look at it, there was nothing there. Not empty space, not even absence. Just something that your shovel could not touch, your eyes could not see, and your instruments could not identify. This is the central mystery of dark matter, not that it exists. That question is, for most physicists, largely settled. The mystery is what it is, and solving that mystery may require not just better experiments, but entirely new ideas about the fundamental nature of matter and force. Let us now step back and consider dark matter not as a mystery to be solved, but as a force that shapes the universe we inhabit. Because even though we do not know what dark matter is made of, we know with remarkable precision what it does. And what it does is nothing less than build the cosmos. To understand this, we need to go back to the very beginning. Not the beginning of the dark matter story as told by human scientists, but the actual beginning, the origin of the universe itself. In the first fraction of a second after the Big Bang, the universe was a seething incandescent plasma, an ocean of energy so hot and so dense that no atoms could exist. Protons and electrons roamed freely, colliding constantly with photons, the particles of light. This constant interaction meant that ordinary matter and light were coupled together, locked in a frantic dance where any slight clumping of matter would be immediately smoothed out by the pressure of radiation pushing back. Ordinary matter could not collapse under its own gravity because the photons would not let it. But dark matter was different. Dark matter does not interact with photons. It does not feel the pressure of radiation. And so, while ordinary matter was being buffeted and smoothed and held in place by the intense radiation of the early universe, dark matter was free to do something extraordinary. It was free to collapse. Under the influence of gravity alone, dark matter began to clump. Tiny fluctuations in density, minuscule variations that may have originated as quantum fluctuations during cosmic inflation, were amplified by gravity. Regions with slightly more dark matter attracted more dark matter from their surroundings. Those regions grew denser. Their gravitational pull grew stronger. They attracted more matter still. Over hundreds of millions of years, these tiny seeds grew into vast structures, enormous halos of dark matter spanning millions of light years. And then, roughly 380,000 years after the Big Bang, something happened. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. When this happened, the photons were suddenly free. They decoupled from matter and streamed across the universe, eventually cooling and stretching into the faint microwave glow we detect today as the cosmic microwave background. And with the photons gone, the ordinary matter was finally free to fall. It fell into the gravitational wells that dark matter had already prepared. Think about this for a moment. Ordinary matter did not build its own cradles. It fell into cradles that dark matter had already built. The dark matter went first. It laid down the scaffolding, the framework, the architecture. And then ordinary matter, released from the grip of radiation, flowed downhill into the dark matter's waiting arms and began to form stars and galaxies. This is one of the most remarkable and humbling ideas in all of cosmology. The galaxies we see, the stars we study, the planets we live on, they exist not because ordinary matter organized itself, but because dark matter organized it. We are living in a structure that was built by something we cannot see, shaped by forces we do not fully understand, guided by an invisible hand that has been at work since the earliest moments of creation. Imagine a sculptor who works in absolute darkness, shaping a block of clay with hands you can never see. When the lights finally come on, you see the sculpture, beautiful, intricate, detailed. But you never see the sculptor. You only see the result of their work. The galaxies are the sculpture. Dark matter is the sculptor. And we are tiny observers standing on the surface of the clay, marveling at the form of the thing we stand on, unaware that it was shaped by something we cannot perceive. The cosmic microwave background, that ancient light from 380,000 years after the Big Bang, provides one of the most precise confirmations of this picture. It is not perfectly uniform. It contains tiny fluctuations in temperature, variations of about 1 part in 100,000. These fluctuations are the fingerprints of the density variations that existed in the early universe, the seeds that would eventually grow into galaxies and galaxy clusters. When cosmologists analyze the pattern of these fluctuations, they find something remarkable. The fluctuations have a specific statistical structure, a pattern of peaks and valleys in what is called the angular power spectrum. This pattern encodes information about the composition of the early universe, including how much ordinary matter there was, how much dark matter, and how much dark energy. And the pattern is exquisitely sensitive to these parameters. If dark matter did not exist, the pattern would look completely different. The peaks would be in the wrong places, the ratios would be wrong. The entire structure of the cosmic microwave background would be inconsistent with what we observe. But when you include dark matter in the calculation, in precisely the right amount, the predicted pattern matches the observed pattern with extraordinary precision. It is one of the great triumphs of modern cosmology, a confirmation that our understanding of the early universe, strange as it may seem, is fundamentally correct. This leads us to a picture of the universe that is both beautiful and deeply strange. On the largest scales, matter in the universe is not distributed randomly. It is organized into a vast, intricate structure known as the cosmic web. This web consists of long, thin filaments of dark matter connecting dense nodes where galaxy clusters form, with enormous voids, regions of nearly empty space, in between. The filaments are like the strands of a spider's web, thin and delicate but spanning hundreds of millions of light years. The nodes are like the intersections where the strands meet, concentrations of mass where the largest structures in the universe reside. And the voids are the spaces between the strands, vast bubbles of emptiness that can be hundreds of millions of light years across. Ordinary matter traces this web. Galaxies form along the filaments and at the nodes, where the dark matter is densest. The distribution of visible matter in the universe is a map of the underlying dark matter structure. Just as the lights of a city at night trace the pattern of its streets and buildings. Remove the streets and buildings and the lights have no pattern. Remove the dark matter and the galaxies have no structure. Computer simulations of cosmic structure formation, massive calculations that track the evolution of millions or billions of dark matter particles under the influence of gravity, reproduce this web with stunning fidelity. The Millennium simulation, the Illustris TNG simulation, the Bolshoi simulation. These and others have shown that starting from the tiny density fluctuations observed in the cosmic microwave background and evolving them forward under the laws of gravity, including dark matter, you get a universe that looks remarkably like the one we actually see. The simulations produce galaxy clusters, filaments, voids, and a cosmic web that matches observations in detail. But here is where things get interesting, because the agreement is not perfect. And the imperfections, the places where theory and observation do not quite match, are among the most exciting frontiers in dark matter research. One of the most persistent discrepancies is known as the missing satellites problem. Dark matter simulations predict that a galaxy like the Milky Way should be surrounded by thousands of small dark matter halos, each one capable of hosting a small dwarf galaxy. But when astronomers counted the dwarf galaxies orbiting the Milky Way, they found far fewer than the simulations predicted. For years, this was a genuine puzzle. Were the simulations wrong? Was the dark matter model incorrect? Or were the dwarf galaxies there but somehow invisible? It turns out the answer is mostly the third option, with some help from the second. Improved surveys have discovered many more dwarf galaxies around the Milky Way than were previously known, many of them extremely faint and hard to detect. And improved simulations that include the effects of ordinary matter, the complex physics of gas cooling, star formation, and supernova explosions show that many of the predicted dark matter halos would indeed fail to form visible galaxies. The ultraviolet light from the first stars would have heated the gas in these small halos, preventing it from cooling and forming stars. Supernova winds from early star formation would have blown out the remaining gas. These halos would exist but would contain little or no visible matter. They would be dark galaxies, halos of dark matter orbiting the Milky Way with no stars to betray their presence. This is a hauntingly beautiful idea. There may be thousands of invisible galaxies orbiting our own, ghost galaxies made entirely of dark matter, moving through space, exerting gravitational influence, but utterly invisible. You cannot see them. You cannot photograph them. But they are there. They are real. and they are shaping the dynamics of our galactic neighborhood in ways we are only beginning to understand. Another discrepancy is the core cusp problem. Simulations of dark matter predict that the density of dark matter in the centers of galaxies should rise steeply, forming a sharp peak or cusp. But observations of many small galaxies suggest that their dark matter density profiles are flatter, forming a gentle core rather than a steep cusp. This could mean that dark matter particles interact with each other in ways that the simplest models do not account for, scattering off each other and spreading out the density in the centers of galaxies. Or it could mean that the complex physics of ordinary matter, the explosions of supernovae, the inflows and outflows of gas, the energetic processes associated with star formation, are reshaping the dark matter distribution in the inner regions of galaxies. This is an area of active research, and the answer is not yet clear. There is also the too big to fail problem, a wonderful name for a serious scientific issue. Simulations predict that the largest dark matter subhalos, orbiting a Milky Way-like galaxy, should be massive enough to host visible galaxies. But the observed satellite galaxies of the Milky Way are less massive and less dense than these predicted subhalos. Either the simulations are overproducing massive subhalos, or the physics of galaxy formation is suppressing the visible properties of these satellites in ways we do not fully understand. These are not crises. They are not evidence that the dark matter paradigm is wrong. They are the frontier. They are the places where our understanding is incomplete, where new physics might be lurking, where the interplay between dark matter and ordinary matter produces effects too subtle and complex for our current models to fully capture. And they are a reminder that even our best theories are approximations, works in progress, maps that are being refined with every new observation and simulation. Let us pause here and reflect on something that does not get discussed often enough in science videos. The sheer audacity of what we are doing. We are a species that evolved on a small rocky planet orbiting a medium-sized star in an unremarkable corner of a galaxy that is one of hundreds of billions. We evolved to find food, avoid predators, and navigate a landscape measured in kilometers. Our senses were honed by natural selection to perceive a narrow slice of reality, the visible spectrum of light, sound waves in a particular range of frequencies, temperature variations on a human scale. We did not evolve to perceive dark matter. We did not evolve to comprehend the structure of the cosmos. We did not evolve to think in terms of billions of light years or billions of years. And yet, here we are. Using mathematics, instruments, and sheer stubbornness, we have deduced the existence of something that makes up most of the matter in the universe, something that is completely invisible to every one of our senses, something that pervades every galaxy, every cluster, every corner of the cosmos, and yet passes through our bodies, through our planet, through our star, without leaving the slightest trace. If you're in a room right now, dark matter is passing through you at this very moment. Millions of dark matter particles, whatever they are streaming through your body every second. They are passing through the walls, through the floor, through the earth beneath you. They are everywhere, and you cannot feel them. You cannot sense them. You cannot detect them even with the most sophisticated instruments humanity has ever built. This raises a philosophical question that I think is worth taking seriously. How much of reality is invisible to us? We know that our senses perceive only a fraction of the electromagnetic spectrum. We cannot see radio waves, microwaves, infrared light, ultraviolet light, X-rays, or gamma rays. We have built instruments to detect all of these, and each new window on the electromagnetic spectrum has revealed aspects of the universe we never knew existed. Radio telescopes showed us the cosmic microwave background. X-ray telescopes revealed the hot gas in galaxy clusters. Infrared telescopes allowed us to peer through the dust clouds that obscure the centers of galaxies. But dark matter represents something deeper. It is not just a part of the electromagnetic spectrum we have not looked at. It does not interact with the electromagnetic spectrum at all. It is fundamentally invisible. And the only reason we know it exists is because of its gravitational influence on the things we can see. What else might be out there, influencing the universe, shaping its evolution, but leaving no trace that our instruments can detect? This is not idle speculation. It is a legitimate scientific question. If the universe contains one form of matter that is completely invisible to us, it is at least possible that it contains others. There could be entire sectors of physics, entire families of particles and forces that interact with our world only through gravity, or perhaps not even through gravity. There could be aspects of reality that we are not merely failing to detect, but that we are in principle incapable of detecting with any instrument we could ever build. This is a humbling thought, and it stands in productive tension with the extraordinary success of the scientific method. On one hand, we have, through reason and experiment, uncovered an invisible component of the universe that constitutes most of its mass. On the other hand, the very existence of that invisible component reminds us that our understanding is fundamentally limited, that the universe is under no obligation to make itself fully known to us. There is a metaphor I find useful here. Imagine a fish living in the deep ocean. The fish knows its world. It knows the water, the currents, the pressure, the other fish. It has evolved to navigate its environment with exquisite precision. But it has no concept of the surface. It has no concept of air. It has no concept of the sun that warms the water, or the moon that drives the tides, or the vast world that exists above the surface it has never seen. We are that fish. We navigate our world with great skill. We build telescopes and particle accelerators and gravitational wave detectors. We measure the cosmic microwave background to 1 part in 100,000. We trace the orbits of galaxies billions of light years away. But we are aware, at some level, that we are swimming in a small corner of reality, and that the surface above us, if it exists, is something we may never reach. Dark matter is a reminder that the surface exists. Now, let us turn to the future. Where does the search for dark matter go from here? The next decade promises a remarkable array of new experiments and observations. On the direct detection front, the next generation of liquid xenon experiments, including XORON NT, LZ the Lux Axelec, IPASI Deluxe X7 experiment, and Panda X4T, are already taking data or will soon begin. These experiments use even larger volumes of xenon, even more sensitive detectors, and even more sophisticated analysis techniques. They are approaching what physicists call the neutrino floor, a sensitivity threshold below which the experiments will start detecting neutrinos from the sun and the atmosphere. These neutrinos will create a background that looks similar to a dark matter signal, making the search even more challenging. But the experiments are being designed to distinguish between neutrino interactions and potential dark matter signals, and there is still significant parameter space to explore before the floor is reached. On the Axion front, the ADMX experiment continues to scan through different frequency ranges. And new experiments like Haystack, Argan, and others are extending the search into higher mass Axion territory. Some of the most innovative proposals involve using quantum sensors, devices that exploit the strange properties of quantum mechanics to achieve sensitivities that would be impossible with classical technology. On the indirect detection front, astronomers are searching for the products of dark matter annihilation, or decay. If dark matter particles are their own antiparticles, as many WIMP models predict, then when two dark matter particles meet, they can annihilate each other and produce gamma rays, neutrinos, or other detectable particles. Telescopes like the Fermi Gamma Ray Space Telescope and the upcoming Cherenkov Telescope Array are scanning the sky for excess gamma ray emission from regions where dark matter is expected to be densely concentrated, such as the center of the Milky Way or the centers of nearby dwarf galaxies. There have been tantalizing hints an excess of gamma rays from the galactic center, observed by Fermi, has been debated for years. Some analyses suggest it could be a signal of dark matter annihilation. Others argue it can be explained by a population of rapidly spinning neutron stars called millisecond pulsars. The debate is ongoing, and new data may eventually resolve it. On the cosmological front, next-generation surveys like the Vera C. Rubin Observatory, named, fittingly, after the astronomer who first provided compelling evidence for dark matter in Galaxies, the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, will map the distribution of dark matter across vast volumes of the universe with unprecedented precision. By measuring the shapes of billions of galaxies and detecting the subtle distortions caused by gravitational lensing, these surveys will create three-dimensional maps of the dark matter distribution, revealing the structure of the cosmic web in exquisite detail. These maps will not just confirm what we already know. They will test our models at new levels of precision. They will look for deviations from the predictions of the standard cold dark matter model. And if they find deviations, those deviations will point us toward new physics, new properties of dark matter, new interactions, new behavior. There is also the possibility that dark matter will be produced in a laboratory. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, has been searching for dark matter particles since it began operating. If dark matter particles interact with ordinary matter through the weak force, then high-energy collisions between protons at the LHC might occasionally produce them. These particles would escape the detector without leaving a trace, but their absence would be detectable as missing energy, a signature that the energy books do not balance, that some of the energy from the collision has disappeared into something invisible. So far, no definitive signal has been found, but the LHC is being upgraded to achieve higher energies and higher collision rates, and future colliders, if they are built, will extend the search further. The proposed future circular collider, a ring 100 kilometers in circumference that would dwarf the LHC, could probe energy scales where heavier dark matter candidates might be produced. But I want to be honest about something. There is no guarantee that any of these experiments will find dark matter. It is possible that dark matter interacts with ordinary matter so weakly that no direct detection experiment will ever observe it. It is possible that dark matter particles are too light or too heavy for our colliders to produce. It is possible that dark matter does not annihilate or decay in any way that produces detectable signals. It is possible that the identity of dark matter will remain a mystery for decades, or centuries, or forever. This is not a comfortable thought, but it is a real one. And it points to a deeper truth about the relationship between human beings and the universe we inhabit. We are problem-solving creatures. We are driven by a deep, almost biological need to understand, to explain, to find the answer. And we have been spectacularly successful at this for the past few centuries. Building a scaffold of knowledge that has taken us from campfires to space stations, from alchemy to the periodic table, from myths about the stars to gravitational wave astronomy. But the universe does not owe us answers. There may be questions that are real, important, and well posed, but that we simply cannot answer with the tools available to us. Not yet. Perhaps not ever. And dark matter might be one of them, or it might not. That is the other possibility, and the one that keeps thousands of physicists going to work every day. The answer might be just around the corner. The next experiment might find it. The next survey might reveal it. The next theoretical breakthrough might explain it. History is full of problems that seemed intractable until they weren't. The nature of the atom, the origin of disease, the mechanism of heredity, all of these were once complete mysteries, and all of them were eventually solved, often in ways that no one could have predicted. Dark matter could be like that. One day we might look back on this era as the time when humanity knew that something invisible dominated the universe, but had not yet figured out what it was. And the answer, when it comes, might be startling. It might rewrite our understanding of particle physics. It might reveal new forces of nature. It might show us that the universe is stranger and richer than we ever imagined. Let me share one more idea with you before we close, because I think it captures something essential about the dark matter story. Something that goes beyond physics and touches on what it means to be a curious species in an incomprehensibly large cosmos. There is a concept in philosophy called the allegory of the cave, from Plato. In this allegory, prisoners are chained inside a cave, facing a wall. Behind them, a fire casts shadows on the wall, shadows of objects that pass between the fire and the prisoners. The prisoners have never seen the objects themselves. They have only seen the shadows. And they believe the shadows are reality. The shadows are all they know. One day, a prisoner is freed and turned around. He sees the fire. He sees the objects. He stumbles out of the cave and sees the sun, the actual world, in all its blinding, overwhelming complexity. He realizes that what he thought was reality was only a shadow of reality, a projection, a dim and distorted echo of something far more vivid and complete. I think dark matter is our shadow on the wall. We see the galaxies. We see their rotation curves. We see the bending of light. We see the cosmic microwave background. We see the cosmic web. These are the shadows. They are real. They are meaningful. They tell us something true about the universe. But they are shadows of something we cannot see directly, something vast and pervasive and fundamental that lies just beyond the reach of our perception. We have not yet turned around. We have not yet seen the fire, but we know it is there. We can feel its warmth. We can see its light flickering on the wall. And slowly, painstakingly, experiment by experiment, observation by observation, we are inching our way out of the cave. Consider the grandeur of what we have already achieved. A species that has existed for a few 100,000 years, on a planet that has existed for a few billion, in a universe that has existed for 13.8 billion, has deduced, from nothing more than the way light bends and stars orbit, that most of the matter in the cosmos is something entirely invisible and unknown. We have measured its abundance to within a few percent. We have mapped its distribution across billions of light years. We have simulated its role in building the structures we call home. We have done all of this without ever touching it, seeing it, or identifying it. This is not a failure. This is one of the most extraordinary intellectual achievements in the history of our species. And the fact that the mystery remains unsolved does not diminish that achievement. It elevates it. Because it means the story is not over. The greatest discoveries may still lie ahead. There is something else that I think deserves attention. Something about the way dark matter challenges not just our physics, but our very intuition about what is real. We live in a world where reality is, for most people, synonymous with perception. Something is real if you can see it, touch it, measure it with your instruments. And for most of human history, this was a reasonable assumption. The world was what you could perceive. And the limits of perception were the limits of reality. But dark matter shatters that assumption. Here is something that is undeniably real, something that shapes the structure of the cosmos on the largest scales, something without which our galaxy, our solar system, our planet, and we ourselves would not exist. And yet it is completely imperceptible. It defies every sense we have. It eludes every instrument we have built. It exists in the most profound and consequential way imaginable. And yet it is invisible. This should change the way we think about reality. Not in some vague, hand-waving, mystical sense, in a rigorous, scientifically grounded sense. The universe is not obligated to be perceptible. The universe is not obligated to be intuitive. The universe is not even obligated to be comprehensible. It simply is what it is, and our task, our extraordinary, humbling, exhilarating task, is to figure out as much of it as we can, knowing that some of it may always remain beyond our reach. There is a beautiful irony in the dark matter story. We look up at the night sky, and we see light. Stars, galaxies, nebulae, all shining across the void. And we think that the universe is a place of light. But the truth is almost exactly the opposite. The universe is a place of darkness. Most of its matter is dark. Most of its energy is dark. The luminous matter, the matter that shines, the matter that makes up everything we can see, is a thin, bright minority. We are the exception. We are the anomaly. We are the tiny fraction of the cosmos that happens to interact with light. And yet, from this tiny fraction, we have reached out and touched the darkness. We have inferred its presence. We have measured its influence. We have begun to map its structure. We are creatures of light, studying a universe of darkness, and we are making progress. That is perhaps the most remarkable thing of all. I want to close with a thought about what dark matter means, not for physics, but for us, for our sense of place in the universe, for our understanding of what it means to be human in a cosmos that is overwhelmingly vast, overwhelmingly dark, and overwhelmingly strange. Every culture in human history has looked up at the stars and asked questions. What is out there? What is it made of? Why does it move the way it does? These questions are not just scientific, they are existential. They are the same questions that drive a child to ask why the sky is blue, that drive a poet to write about the moon, that drive a philosopher to wonder about the nature of being. Dark matter is the latest chapter in this ancient story. It is a reminder that the universe is deeper than we thought, stranger than we imagined, and more mysterious than we can easily bear. But it is also a reminder that we are capable of extraordinary things, that a species that evolved on the savannas of Africa can deduce the existence of invisible matter in galaxies millions of light years away, that curiosity is not just a luxury, but a survival mechanism of the highest order, that the drive to understand is not a weakness, but a strength, perhaps the greatest strength our species possesses. We do not know what dark matter is. We may not know for a long time, but we know it is there. We know it matters, and we know that the search for it is one of the noblest and most thrilling endeavors in all of human history. So the next time you look up at the night sky, remember this. What you see is beautiful, but what you cannot see is holding it all together. The invisible hand of dark matter shaped every galaxy, guided every filament of the cosmic web, and built the scaffolding upon which the visible universe hangs like ornaments on a tree. You are looking at 5% of reality. The rest is hidden. The rest is dark. The rest is waiting to be understood. And somewhere, right now, in a laboratory deep underground, in an observatory on a mountaintop, in an office filled with equations and coffee cups, someone is trying to find it. Someone is listening for the faintest whisper of the invisible. Someone is reaching into the darkness, guided by nothing more than mathematics, patience, and the unshakable human conviction that the universe, for all its vastness and mystery, is not beyond our comprehension. They may not find the answer today. They may not find it in their lifetime, but the search continues. It has continued for nearly a century, and it will continue for as long as there are human minds curious enough and stubborn enough to ask the question, what is the universe made of? We are closer to the answer than we have ever been. And the darkness, vast and silent and patient, is waiting.